Okay, let's do Chapter 2, Section 5, Compound Inequalities. And we're going to start out with a definition about two sets. So let A and B denote two sets. So those are just shorthand for two sets. Then the intersection, and that's the word that's being defined here, so I will underline it, of A with B, which is denoted. Denoted is just another word by telling you that's how we're going to symbolically write it. A, and the symbol for intersection is going to be an upside down U, and it's going to be read A intersect B, or the intersection of A with B. Well, that is simply all elements which are in both the set A and the set B. So symbolically, or visually rather, we can denote it if I have, this is set A, and this will be set B. Then the intersection, so let me again, so basically I'm just letting a circle. So this is set A, and this circle will be set B. So anything within the boundary of a circle, just conceptually, is in the set A, and anything in the boundary of B circle is in the set B. So the intersection of set A and B is just this area right here, because anything in this area is contained in the circle A, and anything in this area is also contained in circle B, so that's both of them. But that's just the visual help. Let's actually look at a specific problem so you can see just how this works out. So let's look at example 1. Different color maybe. So let A be, this is the set. So let's see if we can figure out what's in A. So A in this case is just denoting, is just a name of a set. So X, remember X stands for real numbers. The vertical bar is read such that those real numbers, I'm going to use are because it's better sounding than is, are even and between 0 and 10. So that's called set builder notation. And for B, I'm literally just going to give you the set. B is equal to 3, 4, 5, and 6. Now I'm going to ask you, list in this type of notation, just set list notation, the intersection of A with B. So it's going to help us out if we rewrite A. So let's rewrite the set A in just list notation. So it's all elements X, real numbers X, such that those real numbers are even and between 0 and 10. Now here, I guess I should say inclusive. So it's uncertain if it's between 0 and 10, not including 0 and 10, or including 0 and 10. Actually, we have a way to disambiguate that now. If you remember from last class, this interval is all real numbers between 0 and 10, including 0 and 10. And this interval here are all real numbers between 0 and 10, excluding 0 and 10. Now, I don't remember if I just made up this example or not. I may have. Can't remember. It's been a while. So let's just pretend that I'm doing exclusive. In other words, 0 and 10 are not included. So they're even numbers, so that means they're whole numbers divisible by 2. So 2, 4, 6, and 8. And 0 is not in there, and 10 is not in there because I'm excluding those numbers. So here's my set A, and here is my set B. So the intersection of A and B are elements which are common to both. Well, let's start with my element of B. 3 is in B, but 3 is not in A, so that's not in the intersection. 4 is in B, and 4 is also in A, so 4 is in there. 5 is in B, but clearly not in A. 6 is in B, and also in A. So the intersection with A and B is just the single two elements, 4 and 6. Notice that the intersection may be empty. It might very well be the case, depending on the sets, that the intersection of A and B contains no members at all, in which case we denote that by the intersection of A with B is the empty set. So let's go ahead and solve compound equalities containing the word and. I've been kind of listening to my videos, and I've tried to adjust the volume, and I have an air conditioner right there in the window, and I forgot to turn it off. I usually do, so I just turned it off. So hopefully any background noise that might be annoying to some of you I can keep down. So let's look at objective 2, solving compound equalities containing the word and. But first I actually tell you what a compound inequality is. A compound inequality are two or more inequalities connected either explicitly or implicitly by the word and or. So those are two words, and the other word is or. And we're going to do the one with and right now. Hence, the solution set to compound inequalities must contain all numbers which make each inequality true. And what makes each inequality true is going to depend upon whether we have and or. Recall, solution sets can contain exactly one number, more than one number, or no numbers at all, the empty set. So let's go ahead and let's look at how we're going to do this one. So my basic suggestion is when we solve compound inequalities, we actually draw two number lines. Some of you can just do it just plain old thinking, but we're actually going to do it by drawing number lines. So we have inequality 1, x minus 7 is less than 2, and 2x plus 1 is less than 9. So here is the deal. When you see the word and, that's going to translate into intersection, the upside down U, but think intersection. So what I do is I'm going to come over here and I'm going to solve this inequality. It's going to be really simple because all I have to do is move the minus 7 to the other side, and I get x is less than 7 plus 2, so x is less than 9. Over here I'm going to start out by moving the minus 1 to the other side. It becomes minus 1. So that's going to give me 2x is less than 8. Now 2 is positive, so when I divide through by 2, I don't have to flip the sign. So that tells me x is less than 4. So now what I'm going to do is I'm literally going to write two lines right above each other. They try to be parallel, but these are just two different number lines. And on the first line, I'm going to put 0 right here. You don't have to. Actually, I'm not going to do that. So I'm just going to look right here at the first one. I'm going to say, okay, for this case, we have x less than 9. So I'm going to pretend that this spot right here is 9. And I'm going to graph the solutions to x less than 9. So remember, these lines go on and on forever to plus infinity and to minus infinity. So right here is 9, and x is less than 9. So I'm going to graph the solution set of that one on the top line. Now I'm going to come over here and graph the solution set to the second inequality where x is less than 4. So again, I'm going to just say, okay, 4. I'm just going to pretend that 4 is right here. And I'm going to graph all values x less than 4 right here. So here's what we do. I've visually got everything I need to do to write the solution set to this. And I'm going to write the solution set as an interval. So clearly, what I'm looking for are places where I have squiggly lines in the top and in the bottom. And that's starting from minus infinity up to 4, but not including 4. This part over here, I don't have a squiggly line in the top and the bottom, so it doesn't count. And over here, I don't have any squiggly line at all. So that's my solution set to this compound inequality. The solution set are all x in the open interval minus infinity to 4. Not so bad. You get to draw pictures. So the next one. So remember, whenever we have the word and, the understood set operation is intersection. So I'm going to graph 2x is greater than or equal to 0. That's going to be one inequality I'm going to solve. And the other is going to be 4x minus 1 is less than or equal to minus 9. So over here, literally, I have the variable term on one side already, and the constant term on the other. 2 is greater than 0, so I can divide through by both sides by 2 without flipping the inequality, and that gives me x is greater than or equal to 0 divided by 2 is perfectly fine. That's not division by 0. 0 is in the numerator, and that's absolutely fine. This is literally equivalent to 0 times 1/2. And I'm going to solve this over here. So 4x, I'm going to move the negative 1 to the other side. It becomes a positive 1. So I have 4x is less than or equal to minus 8. It doesn't matter that the constant term is minus. What matters is the coefficient on the variable x. So that gives me x is less than or equal to minus 2. So now I'm going to graphically denote both of these on a number line. And it's just going to be understood that these go on forever. And forgive me if they're not perfectly parallel, but this is just to help. So I'm going to first graph this one. And I'll use the top line. You can put it down here if you wish. So I've got to decide where 0 is on my line, and I'm just going to arbitrarily say that's 0. Whoops. I got to change to my pen. And then I'm going to arbitrarily decide where minus 2 is. And I'm going to say, well, it has to be to the left of my 0. but that's okay. And now I'm getting ready to write in the solution. So x is greater than or equal to 0. That's the same thing. So x is greater than or equal to 0. So to include the fact that 0 is included, I'm going to draw that. So that's the solution set on the top line. And down here, x is less than or equal to minus 2. And what is my solution set? My solution set is the set of all areas with squiggly lines in both lines above and below each other. And there is no area of the line where there's a squiggly line below and above at the same time. So remember, this is where x satisfies this inequality, and this is where x satisfies this inequality. So our solution set is empty. There are no numbers that satisfy both of those inequalities, and I'm almost certain that's the symbol that my math lab will want you to use. Another common symbol for the empty set is just that right there, and you may have seen that in an earlier class, granted that you've had these concepts before. Okay. So exercise 4. Solve 2 is less than 4 minus x, which is less than 7. Hint, use the addition and multiplication properties to get x is less than b but greater than a. And that's exactly what we're going to do. So this is literally a compound inequality, because if I can get it to this form right here, then x has to be greater than a, and, there's the hint, and, less than b. So that's what we'll do. So let's see what our problem says, and our hint to solve it. So we have 2 is less than 4 minus x, which is less than 7. That minus is annoying, right? It's going to cause us some problems, but we can deal with them. So what I want to do is I want to subtract 4 from each piece. In other words, before I start, this is identical to the following. Our two inequalities is that 2 is less than 4 minus x, and 4 minus x is less than 7. Now, if you want to just treat those two as two separate inequalities, you can, but there is an easier way. We're just going to treat all three of them together, and I'm going to start down here. Do so by subtracting 4 from each piece. This piece, this piece, and this piece. So that's going to give me 2 minus 4 is less than 4 minus x minus 4, which is less than 7 minus 4. So I just use the addition principle. So 2 minus 4 gives me minus 2. 4 minus x minus 4 is the same as 4 minus 4 minus x. That just leaves me a minus x. And then that leaves me a 7 minus 4, which this is 3. So this, unfortunately, has a negative x in it. So what I'm going to do is multiply all three sides of this inequality by a minus 1. So that's going to minus 1 times minus 2 is 2. But when I do so, I have to flip each inequality sign. So I have x is now greater than minus 3 but less than 2, which is normally written as this way, is x is greater than 3, this is my x, and less than 2. So that's my x. So now we can go ahead and graph that. X is greater than minus 3 but less than 2. So 2 lines. Doesn't really matter which color they are. So literally, to be honest with you, you should easily, from my interval notation from last time, easily be able to show immediately this is minus 3 and 2. But let's go ahead and translate that. This says that x, on the one hand, x is less than 3, and on the other hand, x is less than 2. And I'll show you we're going to get the exact same thing. So I'm going to put 2 here and minus 3 here. Minus 3 and 2. So x is greater than minus 3. Minus 3 is not included. So I get all of this area up here going on to infinity. Here x is less than 2. 2 is not included. So I go everywhere down here. And what is the area that have squiggly lines in both the upper line and the lower line? Well, I don't include 3, but I go all the way to 2. So you see, we literally get the exact same solution. So here we go again, very, very similar to the other one. And we're just going to go ahead and use the first method of solving it. It's so much easier because once you get it into a certain form, for example, this form right here on the previous one, it's easy to go from there to interval notation by what we learned in a previous class. So here I have 5. So I have minus 1 is less than or equal to 2x divided by 3 plus 5, which is less than or equal to 2. So again, we're going to use our clearing denominator method. And we're going to treat this like it was one gigantic equation. Now I'm going to multiply everything by a 3. So, and use distribution. So 3 times minus 1 is minus 3. 3 times 2x divided by 3 is the same as 3 divided by 3, which is 1, times 2x. But I have to do it also with the 5. You can't forget the 5. 3 times plus 5 is plus 15. And 3 times 2 is 6. So that's my new inequality. So here again, we're going to go ahead and I'm going to subtract 15 from all 3 sides. So minus 3 minus 15. Why am I doing that? So I can isolate the 2x term in the middle. So this gives me minus 18 down here. And 6 minus 15 is minus 9. So what do I need to do? I have 2x in the middle, so I'm going to divide through everything by 2. 2 is a positive number, so there is no flipping of the inequality signs. So that's going to give me minus 18 divided by 2 is minus 9. 2x divided by 2 just leaves me x. And minus 9 divided by 2 we're going to leave that as just minus 9/2. You can write minus 4.5 if you want, but from here I can easily see from interval notation that x is greater than or equal to minus 5, but less than or equal to minus 9/2. Okay, not too bad. So objective 2, we can live with that, I believe. So objective 2 is going to be solving compound inequalities containing, well, we're on objective 3, finding the union of two sets. I say it's objective 2, that's just a typo. I'll eventually fix it. So the union of two sets. So let's look at the union of two sets. So the union of two sets is really similar to the intersection of two sets. So let A and B be two sets. The union, and that's our word that's being defined, of A with B is another set that contains all elements in A and all elements in B. So another word to say that is if X is an element in the set A, or if X is an element in B, then that element X is in their union. So how do we denote the union of two sets? Well, have A and I have B, and the symbol for union is just a U. There isn't a little bitty down thing, it's just a U that looks like that. And symbolically, if this is set A and this is set B, can you guess what the union of those two sets are? Well, notice anything in the boundaries of A is in their union, and anything in the boundaries of B is in the union. So literally we have that's the union of A with B. So it's a bigger set. And the only time the union of A with B is empty is if both A and B are empty. So do I have an example here? Yeah, let's do this again. Let's look at the exact same examples that we had earlier and take their union rather than their intersection. So A was the set that contained 2, 4, 6, and 8. And B is given to you there. B is equal to 3, 4, 5, and 6. So the union of A with B is another set. And what do I put in that set? Everything in A and everything in B. So sets aren't ordered. So 3 is in there, 2 is in there, 4 is in there. It doesn't matter that 4 is in both. 5 is in there, 6 is in there, and 8 is in there. So it doesn't matter. And you don't want to list elements twice. You can, but it's just confusing. A set is made up by its element. So if 4 is listed in there twice, you just got the same element in there. It doesn't change the set. So that's the union with A and B. So let's take a look, and let's solve compound inequalities with OR. Just as before, we'll use our graphical approach to help us out until you get the hang of it. Now, many of you have abstract thinking abilities, quite advanced, and you don't necessarily have to use this method of drawing pictures. But for those, many of you who don't have highly developed abstract mathematical minds, OR, so remember OR denotes union. Pictures are always helpful for the rest of us. So let's solve both of these in turn. So this gives me 5x is less than or equal to 10 plus 3, which is 13. And since 5 is positive, I'm going to divide both sides through by 5. This is going to give me x is less than or equal to 13 fifths. Now notice that 13 fifths is 2 and 3 fifths. And over here, x is less than or equal to, I move the 1 to the other side, it becomes negative 4. So let's draw my two lines. And I will do x is less than or equal to 2 and 3/3, 3/5, sorry. There's a reason I did it that way. And x greater than or equal to 4. When you're finding or locating places on the number line, 13 fifths is kind of hard to know where to put it. But 2 and 3/3, it's going to be 2. So I'm going to say that right here is my 13 fifths, or 2 and 3/5. I think I said 3/3, 3/5. So that's this point right here. And over here, this is 4. So let's do x greater than 4. So x greater than or equal to 4. So 4 is included. It's everything up here. And down here, x is less than or equal to 2 and 3/5. So here we actually run into an interesting conundrum. So this interval is minus infinity to 13 fifths, or if you want to write 2 and 3/5, that's fine, and that's included. And then I'm taking the union of this, and I have 4, which is included, and it goes all the way to infinity. In all of this area right here where there's nothing, this area right here, it's not in the set. So we have no interesting way to write the answer except as the union of two sets. So this is set A, and that satisfies this inequality. This is set B, and that satisfies this inequality. And I simply have to take the union, and that's it. I just had to look outside. I just saw a guy with a kid, and I also just saw a snake go across through there, so I was wanting to see if there was any conflict, and there wasn't. At any rate, let's go on. So let's do number 8. It looks like I'll just have to write it down from my notes. Yeah. So let's do number 8. Come back here. So this is number 8. And I have minus 2x minus 5 is less than minus 3, or 6x is less than 0. So remember, or denotes union. So we're going to solve both of these in turn. So I'm going to do something right here like I've always been doing. I'm going to take the minus 2x and I'm going to put it on, move it over here. So it changes sign. And the minus 3, that means the minus 5 is over here by himself. And the minus 3 I'm going to bring over and it becomes plus 3. And I'm doing that just so I'll have a positive coefficient on my x term. So 3 minus 5 is minus 2 is less than 2x. So now I can divide by both sides by 2. And there is no requirement to flip the inequality. So I get minus 1 is less than x. Or 6x is less than 0. I just divide both sides through by 6. So x is less than 0. So you can again draw 2 quick lines to help you out. And there's nothing wrong with doing that, clearly, or I would not be telling you to do it. And just I'm going to arbitrarily write 2 lines and say one of them is minus 1 and the other is 0. And now I'll do minus 1 is less than x for the top, and x is less than 0 for the bottom. So this tells me that x is greater than minus 1. It's not included. And down here it says x is less than 0, and 0 is not included. Wow. So I'm taking the union of these two sets. So the union is every place, remember these number lines go on forever and ever. So the union is any place on the number line where there is at least one squiggly yellow line in this case. And in that case, the union, I start at minus infinity, I get up to minus 1, and I still have squiggly lines. Then I get up to 0, and I still have a squiggly line, at least in one line, all the way to ever, to plus infinity. So the answer is every real number x solves this compound inequality connected with the word or. So symbolically, that's minus infinity to infinity. And now that you've been introduced to interval notation, it's much easier to write this than x such that x is a real number. That's hashtag for you guys. It's been number for most of my entire life. And of course, the one that you're not taught for any math major in here or computer science major, the symbol, the common symbol for the real numbers is that right there, and it's got that double bar for the R. Our textbook does not use it. Just pay attention to that if you're a major. Other than if you're a STEM major, you'll probably have to use that at some point. Believe it or not, that's it for 2.5. So if you have any questions, just let me know by email or on Teams.